For years, AI integration mostly involved calling an external API, but for production systems that require absolute privacy or real-time data orchestration, that single-track approach is splitting into two distinct paths. In modern systems engineering, the hardware environment no longer just hosts the application, it dictates how the entire system must be built. Architects today are forced to choose between two conflicting strategies for handling model logic. The first strategy pushes inference to the edge. This localizes the model to the user's device to achieve zero-latency processing and absolute data privacy without an internet connection. The second strategy involves orchestrating cloud-native pipelines. This is required when a system must navigate dynamic, multimodal enterprise datasets that change by the minute. Successful deployment now requires moving past model parameters to focus on the hardware trade-offs between these edge and cloud configurations. Choosing the edge means working within a strict physical ceiling. Most modern smartphones cap available memory for specific tasks at roughly 6 to 8 gigabytes. This creates a direct conflict with large language models, which require a massive VRAM footprint to hold uncompressed weights in memory. To bridge this gap, engineers use model quantization. Quantization compresses the model by dropping mathematical precision. It shifts the weights from 32-bit floating point numbers down to 6-bit or 8-bit integers. This allows open models like Qwen 3 or Llama 3.2 to be packaged into GGUF files, highly compressed snapshots that fit onto mobile storage. The cost of this reduction is a measurable loss in reasoning precision, but it creates a memory footprint small enough for consumer hardware. But solving the memory problem is only the first step. The hardware must execute inference calculations without draining the battery or stalling the interface. If you rely solely on a mobile CPU for dense tensor math, token generation becomes too sluggish for a usable experience. To fix this, mobile frameworks offload the heavy compute layers directly to the device's GPU. This is handled through hardware abstraction layers, like Apple's Metal API or Android's NN API. Developers can optimize this further by manually increasing the number of model layers assigned to the GPU, pushing the hardware to its maximum throughput. Implementing flash attention further accelerates the process by optimizing how the system tracks token weights in memory during generation. When you combine quantization with this level of GPU acceleration, you can run fully autonomous, zero-telemetry AI entirely offline. Local inference is highly efficient, but lacks access to dynamic data. It cannot answer questions about information outside its original training set. This is where cloud-native orchestration becomes necessary, as seen in this 2025 research into integrating LLMs with geographic information systems. The goal is to build an assistant that can query a live database of waste management locations and render them on a map in real time. To prevent the model from hallucinating coordinates, the system uses spatial RAG. First, the system ingests geographic data and documents, embedding them into a ChromaDB vector store managed by Llama Index. When a user asks a question, Llama Index retrieves specific, structured GeoJSON data from the database. The model then formats that raw geographic data so it can be understood by the application's front end. This formatted data is then rendered dynamically onto a leaflet map. In this configuration, the LLM acts as a logic controller. It manages the verified data systems rather than attempting to provide the knowledge itself. Moving this spatial RAG architecture into a production environment requires a massive jump in infrastructure. Meta's standards for Llama deployment emphasize the physical mass of cloud architecture required to sustain these pipelines. Architects must implement hardware autoscaling to ensure that latency remains low even when user traffic spikes. Security becomes a primary concern, often requiring virtual private cloud isolation to keep regulated data within a controlled perimeter. There is also the hidden cost of token management, calculating the ongoing expense of processing input, output, and cached data. Cloud orchestration provides the deepest data integration possible, but it introduces significant system complexity and recurring operational costs. AI engineering is defined by optimization. No single model fits every use case. This is reflected in the HSSO thesis benchmarks, which compared different model sizes against specific performance goals. Lightweight models proved most efficient for fast, cost-sensitive routing, while mid-tier reasoning models were necessary for complex retrieval tasks. These architectures are evaluated against three metrics: offline privacy, contextual depth, and compute cost. Edge architectures like PocketPal maximize privacy and offline capability with low costs, but lack contextual depth. Cloud architectures maximize contextual depth, but score poorly on privacy with higher compute requirements. The choice comes down to the application's primary constraint. Edge is for zero telemetry and privacy. Cloud is for real-time synthesis and multi-agent workflows. The best systems architects don't just benchmark parameters. They design the computational physics of the deployment to match the exact operational realities of the user.